And your hat, please, Julian. There it is. So you and your partner will have each have a piece of paper. Both of you have to write out the answers, but I will just grade whichever one's put on top. Okay. You will have a periodic table that I would give you to use for molar masses and things like that. You will be able to use your ion paper and your solubility and reactivity sheets. You will. And obviously a calculator would be very useful. So all of those things. And in addition, you have the opportunity to do a whole piece of paper, handwritten, back and front. I don't care if you want to write all over the place. It's up to you, but your own sheet of notes. Okay. So all of those items will be available for you to use, which can be a benefit, but it can also be a hindrance if you don't know where everything is. Anyway, so what's going to be on there? Mostly it's going to be chapter 10. That was the stuff on moles, calculating molar mass, changing grams to moles, changing volume to moles for gases, and that's also percent composition. And you have a problem that we did on those. Chapter 11 was the stuff we've been spending quite a bit of time on, writing and balancing chemical equations. Knowing what types of equations, what types of reactions, endothermic, exothermic, combustion, synthesis, decomposition, all that stuff. And that also was the net ionic equation stuff. And then the stuff we started Wednesday on stoichiometry, which is what we're doing right now. The ratios and proportions, the mathematics of chemical reactions. Now, I am planning to give you a glancing blow of something called kinetic molecular theory and the properties of gases from chapter 13 on Thursday, and another glancing blow on gas laws, which is in chapter 14. I will make that light and not a lot of it, but I have to hit it a little bit. Because, yeah, you're going on. Okay. There's a lot more we could do if we had more time, but I know you guys want summer too. So focus your energy on these 3 chapters. And hopefully that should be good. Yes, ma'am.
What do you recommend us look at to get the most valuable information?
Honestly, the note sheets I've been giving you.
Okay.
So go back through the classroom because I've given you a lot of note sheets on these.
We've had lectures like that recorded.
Yeah. So, you know, the note sheets are probably blank online, but, you know, scan them and see. All the stuff is since I've been back with you, right? So, and we've been back in person, those of us that are in person. And this stuff won't be heavy. I may ask some questions about, you know, ionic compounds, covalent compounds. I may incorporate it into what you're doing. So, yeah. Congratulations on surviving this year. Okay. I just want to say that we've survived. It hasn't been pretty, but we made it work. And I hope it didn't sour you for science. Yeah. I don't know, like 100 each day. So I don't know, 75, maybe not even 100 points for the first day. So some, and I haven't gotten to grading. So my son came home this weekend so we could cry about our dog dying and take care of that. And I've kind of got some sort of sinus thing going. So I'm way behind still, And they're still messing around with scheduling for next year in summer school, and summer school starts on June 7th, boys and girls, and nobody knows what they're doing. So I apologize for not having grading done.
It's okay.
It's not, but thank you. Yeah. Any other questions? I wish I could give you, I don't have a fixed percent. Sorry to anybody else. All right, let's get this show on the road. Anybody from home have a question? I have a really cool article that I plopped into your feed, and I want to just go through a bit of it, even though it has nothing to do with chemistry. It's still cool science stuff. So you might have seen that there was a big discovery in Calaveras County of ancient fossils, millions of year old fossils. And I just want to point out, this is a tooth. Okay, that's a regular sized piece of paper. Look at the size of that tooth. It's like crazy. So that's a mastodon tooth. And they have these little spiky nubs on them. That's a distinguishing characteristic. Anyway, like big elephant thing with tusk. Yeah, really cool. Over in Calaveras County. So Sierra Nevada mountains, as you know, you probably know, living up here, all of our snow and runoff goes into reservoirs now. Why? Because we need the water during the summer and to prevent flooding downstream. And our water was sold to the highest bidder decades ago to population centers, which of course were towards San Francisco. So Hetch Hetchy is owned by the city of San Francisco, water in there. And then over in Calaveras County, two reservoirs, Pardee and Comanche, are run by the East Bay Municipal Water District, or Utilities District is what it's called. And some of you have probably been to these. Have any of you been up over to Pardee or Comanche? Oh, okay. So Comanche is the bigger. Oh, I didn't want to turn it there. Comanche is the bigger one, I believe. And it is, if you go down Highway 12, so you have to go into San Andreas or towards that end of the world. Anyhow, it's pretty good size, and a lot of people go out there, and it is. It's pretty. Reservoirs are great. Love having them. But again, it was blocked. It says to protect flooding. Well, the Central Valley used to be a big lake. You guys know that, I hope. And that's why it's so flat, because all the sediments. It has 40-foot deep topsoil in places in the Central Valley because all this stuff running off and settling at the bottom. When that ancient lake opened up, the delta happened. All the rivers coming out of the mountains all come down there and flood that area every year. And so we built up the ditches and canals and the stuff that we call the delta. A lot of that is artificially propped up to keep the communities from flooding. Same with the reservoirs, help with that. So yeah, so it used to be a lot of water just coming off of the mountains. Well, during the Miocene, which is part of the Cenozoic, the tertiary period of the Cenozoic, in ancient times, 23.8 million years ago, was when mammals were starting to take over, right? The dinosaurs went extinct, and off we go into mammals. And so now we have these reservoirs to play around in, which is cool, but we have to take care of the reservoirs and inspect them. And one of the things that we do is we send out naturalists out to check what's going on. And this gentleman went out on the Mokelumne River, and I'll let him tell you his story.
The discovery occurred while I was on patrol out on the watershed, and I happened upon a petrified tree. This tree was partially encased in the burial sediments, and because one end was exposed, I could actually see the tree rings inside. So I looked around the area further, and I discovered a second tree, and then a third, and so on. After finding dozens of trees, I began to realize that what I was looking at was the petrified remains of a forest.
So I have a piece of petrified wood that I picked up at a rock show some years ago. And when you look at it, I mean, you can actually, it looks like a piece of wood, and you can come up and look at it at the end. Like, this edge is bark. And then this one, you can actually see the rings. And you've all seen pieces of wood, I'm sure, lying around and cracked and stuff, and you can see the cracks. What happens is when the wood gets smothered with silt and sediment and water, and millions of years go by, and that silt and sediment lithifies. That's just a fancy word for saying it makes a rock. And so it turns into a rock. Petrification is when they turn into a rock. So that porous, fibrous wood ends up getting mineralized and lithified. And he found scads of petrified trees along this watershed, along the river in Calaveras County. So to the average person, you'd look at that and go, oh yeah, that's a brown rock, whoopee. Except you can kind of see some layers, some fibery looking, you know how tree branches look like if you've seen a tabletop or hardwood floors and stuff. You can kind of see it in there. I would walk right over it. I'm thinking it's this thing, but I honestly don't know if it's this thing. But he put his walkie-talkie. It's a classic thing that geologists do. They put something in the picture to give you perspective on size. But one of these lumps is a petrified tree. Okay. And this one's a little more obvious. It looks like a log laying there with his rock hammer. But it's rock. It's not a log. And yeah. Yeah, it's very cool. I love this stuff. I mean, it's like my little geeky part of me. Yeah.
Is there a way that you could speed up that process if we wanted to like
make your own petrification?
Yeah.
I don't know if it's doable in a lifetime. You know, I mean, 100 years is a long time. 200 years, you try and think about 300 or 400 years, you know, that's like hard to even comprehend. And then these are millions of years old. So it's just really like, we can't timeline stuff.
This is in Colorado?
Mm-hmm. And then here's a piece of bone that's part of the rock now too. Bone's kind of rocky anyway, but it has that porosity of bone. If you've ever seen old bleached out bones, like on a hike or something, there's all these openings for the blood supply to go through. Bone is not static. It doesn't stay the same. When you make your bones, they're constantly getting broken down and remade all the time. Okay. And so that you can see the whole, that doesn't say what kind of, it says unknown vertebrate. But anyhow, so the knife is in there for size perspective also. This is some of the, these are some of the critters and artists' rendering of some of the critters that existed in the Miocene. And so this naturalist that you just heard, he called on people from all over the place, including Cal State Chico geologists. I'm not sure if he had a connection with them or not, doesn't really say. This woman is looking at a fish fossil. So fish fossils are kind of hard. They're pretty soft. Any kind of thing that doesn't have a backbone, obviously, is really hard to fossilize too. But this kind of stuff has to happen with a whole bunch of sediment coming down just the right time after the organism has expired. But you can kind of see like tailbone stuff going on here. There's lots of fish, of course, that this is a picture of Chinook salmon trying to come up the Milk River it doesn't say, it says fall Chinook salmon coming up. So they have to have it. We make these reservoirs and then the fish can't go back to the natural breeding ground. So they have to make ladders and things in different places. But there were ancient salmon as well, which they think that fossil was. These guys are so cute. Oh my gosh. Tapirs. This is a baby tapir in Dublin, but there was the other thing about the Miocene, all the animals are like ginormous. Okay. And so here is a baby tapir's jawbone from the Miocene. And you go, what? How do they know that? Yeah, DNA, baby. And this, you guys have probably, some of you anyway, have been on in the dentist and had a 3D scan of your jaw. They took the baby tapir jaw and put it in there and scanned it. It's kind of cute at a dentist's office. But that's just some of them. There's the tooth, this huge tooth. They found a complete skull of a mastodon. They found a camel toe bone. There's a type of camel species, pre-species. Horse teeth. Rhinoceros. Who knew there was a rhinoceros in California? I didn't. Tortoise. This guy's having fun out there with his drilling up a tortoise shell plate. So the bottom plate on the belly plate of a tortoise is one of the things that they found, ancient tortoise.
Those are probably huge. They already are originally pretty big.
They are big. So yeah, it's crazy. And then this is the craziest thing. What in God's name is that? It's a gomphother. It has 4 tusks,
Yeah.
2 up top and 2 at the bottom. I didn't know there was ever such a thing. Anyway, so it's like, you know, your fang teeth grew out straight instead of up, you know. It's
How do they
nuts.
even eat anything?
I don't know. I don't know.
What do they like?
With their
suck up
big ass teeth. That's what it makes it. It's crazy. So here's a, this is a jaw of one of those things. So they wrap them up in plaster. They wrap them up in cloth and then plaster it like a, you know, when you break your arm or your leg or something. And then they have to haul it with a big old lifter. Yeah.
How much would that thing weigh?
A lot. How's that for a good answer? Let me go back to the,
That's just the bone.
yeah, that's just exactly. Where did this one go? Oh, maybe it's later. So the tortoise. So this, they'd found them before. So again, we lose track of things. It's not like this is the first time they found fossils out in that area. When they were first putting the pipe in for the East Bay Municipal Water District in the 40s, 47, they found a mastodon jaw. And when they were digging the trench for the pipe to send it to the bay. But people forget. Oh, I don't have it. Hang on, let me find this. Did I show you this one? Hang on. Anyway, where did it go? No, that's the petrified trees. It's here somewhere. Oh, this one. This is what I want to show you. So here is a mastodon tooth and part of a tusk. So they found the complete jaw. They obviously sawed it because they had to get it out of there. So here they are putting it on a pallet to get it out. And then here they are at Chico. This is where they cut through it, obviously, or maybe it broke there. I don't know, but cleaning it up. And then look at this. This is nuts. That's a single tooth. Oh, that's a big. Kind of. We're all related. We're all mammals. So anyway, Chico State geologists are working on this right now, helping clean it up. They haven't said exactly where it is because they don't want everybody out there destroying it and taking their own fossils. So, but I may have to go hiking this summer. I don't know. Anyhow, it's pretty cool. And I love that kind of stuff. So I just want to share that with you because even though it's not chemistry, it's still cool. It is, yeah. Mm-hmm. Yep. Those of you at home, pull this one up. Those of you in the classroom, I have a hard copy for you. Yeah, Get on it. All right, now I'm going to give you an extra one. Pass that. So we are going to talk about stoichiometry. We got started on it. It's kind of weird, no doubt about it, but it really is the important thing to know how to do in chemistry. So I have to go through this with you. So forgive me for cramming this in your brains at the last bit of school. Okay. So on Friday, we left off with this slide. I told you the only thing that stays constant in chemical reaction are the total number of atoms, reactants and products have to have the same number of atoms on each side. And the mass also stays the same. That's what conserved is. The number of molecules can change because you take apart your pieces and put them together in a different way, right? The number of moles can change. And if you're dealing with gases, if the number of moles change, the space they take up, the volume can change as well. The only thing that stays constant left and right on a chemical reaction is total number of atoms and total mass. This is a reaction with a hydrocarbon turning into carbon dioxide and water. And you all know this is what kind of reaction? Hydrocarbon and oxygen. Good job. Combustion. And so if we were to balance this, which I could make you do, except for I already put the answer on your paper, so it's pointless. The 2 carbons on the left, 1 carbon on the right, obviously isn't balanced. You'd have to throw some coefficients around, and you have to go back and forth a little bit, and that's fine. But the balanced equation looks like this. So this is ethine, which people call acetylene, okay? Properly named in proper chemistry terms, it's ethine. Just carbon and hydrogen with a triple bond. All right, so acetylene torches, welding torches, that's the gas that you use. It combines 2 of these molecules with 5 of the oxygen to make 4 carbon dioxide and 2 waters. If you count atoms, 4 carbons on the left, 4 on the right. 4 hydrogens on the left, 4 on the right. 10 oxygens on the left, 8 plus 2 is 10 oxygens on the right. That stays the same. How they're stuck to each other changes, so you get different numbers of molecules. You also get different numbers of moles of molecules, okay, because you can't just count individual molecules. And since they're all gases, and we know at STP, 1 mole of any gas occupies 22.4 liters. What's STP? Standard temperature and pressure. 0 degrees Celsius, totally impractical, and 1 atmosphere of pressure. All right, so moles, 7 on the left, 6 on the right. That's not equal. Volumes, right? Not equal. But mass is equal. Mass of ethine, 2 carbons, 2 times 12 is 24. 2 hydrogens, 2 times 1 is 2. 24 and 2 is 26. Oxygen, 16 on the periodic table, but oxygen gas is diatomic, 32 grams per mole. This mass and this mass is equal to the sum of this one and this one. The masses stay the same. The number of atoms stays the same. How they stick to each other changes. And so that's the takeaway message. One more time that we ended with on Friday. Questions on that? So you have to recognize what kind of reaction something is. You have to recognize that oxygen is diatomic. You have to recognize that you can calculate the molar mass of a substance. There's a lot of things that you already know how to do, but stoichiometry puts it all together as one single thing. Why is it such a big deal? Because you need to know if you have the right amount of ingredients to make the right amount of product. The example that they have is the chemical reaction that causes airbags to inflate. There's some chemical called sodium azide. It doesn't matter what it is, but you have to have the right ingredients to make the right volume of final product to inflate the airbag properly. Too little reactants, the airbag doesn't inflate enough, you smack your face on the steering wheel. Too much product formed, the airbag explodes and you smack your face on the steering wheel. So you want to have just the right amount of ingredients to make exactly the amount of product that you need. How do you figure that out? Stoichiometry. It's a lot more fun to talk about brownies, so that's where we're going to go next. Okay. So molar mass, you should know how to do that. Calculating molar mass. Converting from moles to grams or moles to liters, you should know how to do that. Okay, that's all stuff, or particles, that's stuff from chapter 10 as well. Writing and balancing chemical equations, that's what we're doing all of chapter 11. Mole ratio, we're going to talk about next. And I'll give you some strategies hopefully tomorrow. Okay, so what are mole ratios? They're going to help you determine from the balanced equation how much reactant you need, how much stuff you got to get out of your cabinet to make the amount of product that you want. Okay, or you want to make this much product, do I have enough stuff? And if I don't have enough stuff, could I make any of my product? Okay. Okay, so the balanced equation is where we get our mole ratios. So mole ratios are the fractions the coefficients from your balance equation. Those coefficients are how many atoms, how many molecules, how many moles of them. It's our proportion. So this is the equation for making ammonia from nitrogen and hydrogen. To go with the recipe analogy, 1 cup of nitrogen gas plus 3 cups of hydrogen gas gives you 2 cups of ammonia. Okay. Which isn't, I mean, we could actually do that because cups are a volume measurement. So we could actually kind of say that. It's really 1 mole of nitrogen goes with 3 moles of hydrogen to make 2 moles of ammonia, right? The only place in the world where 1 plus 3 equals 2 is chemistry, right? So what kind of proportions can we get? Ratios are fractions or proportions, right? 1 nitrogen for every 3 hydrogens. Another way to read that is I will make 1/3 as many nitrogens as I have hydrogens. 2 ammonias per every 3 hydrogens. Again, you can say, I'm going to make 2/3 the number of hydrogen atoms I will make into ammonia. Actually, not hydrogen atoms, hydrogen molecules into ammonia molecules. Okay. Another proportion we can pull out of this is 2 ammonias formed for every 1 nitrogen. I will make twice as many ammonia molecules as I have nitrogen molecules available. Okay. All of these, you could insert the word moles in between the number and the symbols. Okay, those are all proportions that are legitimate. How do we know which one to use? Well, this is on your paper as well. We're going to use the one that gets us from our given information to our asked for. No. Okay, oops, I better leave that on in case somebody comes. So, moles of given substance, whatever it is, times some proportion. Again, this is the coefficients from our balanced equation. Asked for substance over given substance. If you multiply this times this, you'll get the moles of your asked for substance. Of course, you guys know that that's the book uses wanted. I used asked for, so I'm going to change that in there. You're going to start with some number of moles and change it to some other kind of moles, depending on what they're asking you to find. So the other thing that you have to know how to do is take mass, because in real life, we're going to measure things out. I can't see atoms and molecules. I'm going to weigh them out on my balance. Okay, so if I'm going to take the mass of something, that's a number of grams, I have to multiply that by 1 mole per some number of grams. That's the molar mass of that substance. Oh my gosh. And I could stop there, and that's one type of problem that you have to do. You take that answer and put it here, and then multiply it by the ratio. That'll give you the moles of your asked for substance. But again, it's not moles that I want. I want to have liters or grams. So the most common type of problem is mass to mass, but there's others. So the molar mass of your asked for gives you a number of grams of the asked for substance. So there's like 3 little pieces to it. Okay. And there could be a 4th piece because you have to find the molar mass of the substance. There's lots of stuff that goes into these, which is why it's so annoying. All right. So on the back, how do you change it? I made a typo, so just fix this really quick. Step number 1, it says change the mass of G given to the mass of G. Well, that's ridiculous. It's moles. It should be moles. So mass into moles is your first step. Second step, change the moles of one thing into moles of the other. Third step, change the moles of the other into grams of the other. And again, book uses wanted. I use ask for. It doesn't matter to me what you use. It's just a way to get things set up properly. All right, did we get to any of the brownie stuff last week? First 3 questions maybe, or not?
Yeah.
Okay, so we're going to stop this right now and we'll come back to it tomorrow, but let's find this. So again, we got this recipe for making brownies, 2 margarines with 4 eggs, 1.67 flours, 2 sugars, and then I added on 1.5 cups of cocoa powder. If you had 8 eggs, you guys can all read the recipe and figure it out, but we set it up with asked for over given, right? What's the asked for? So this is our abbreviation, 2 M's plus 4 E's, etc. And did we do 1, 2, and 3? Yes? Okay, so let's go to number 4. What if you had 3 eggs? So you have to go back here. Goodness gracious. Me and my elbows. There we go. And you're really hungry and you want to make the most brownies you could. How much flour would you need? So your given information is 3 eggs. You need a proportion with eggs on the bottom and flour on the top. 1.67 flours go with 4 eggs. Okay, how much flour do you need?
Read this information. Oh.
Okay, so you get okay. It's all right. So again, eggs on top, eggs on bottom. We're left with flour. So the asked for is on top. The given is on the bottom. Where do we get those numbers? We got it from the recipe. I guess I should have highlighted this one too. The recipe of our, oh, well, it's not going to highlight it for me. Anyway, so you could do this a couple of ways. You could say, oh, 3 over 4. So what's 3/4 of 1.67? You could do 3 times this and divide the answer by 4. You can multiply by 0.75 if you think in decimals. Amani, did you get it?
I'm trying to.
Okay. Anybody?
So it's 0.75 times 1.6.
You can do it that way. Do 3 times 1.67. Hit enter. So you get an answer and divide by 4. Sure. 1.25 cups of flour is what this one is. Yeah.
Okay.
Okay. And then what if you want to make 3 batches of brownies? How many cups of sugar do you need? This one's easy because I changed the amount of sugar to try and make the recipe taste better. So now it's really easy. I forgot to change this problem. You want 3 batches. That's what you're given. What's the ratio of sugar to batches from the recipe? Go back up here. 2 sugars for 1 batch. Right? So you need 6 cups of sugar. Very good. That's number 5. Okay, number 6 says you have 2.5 cups of flour. So always write the given information, the one that you have a number for first, 2.5 flours. And you want to know how much sugar you need to go with that flour. Like you want to make as much as you can with what you got. You have some ingredient that's limiting your product. So again, for this one, 1.67 is the given substance proportion from my recipe. And then the sugar is also from my recipe. When you have a number that's not in a fraction, you make believe it's over 1. Things on top cancel things on the bottom. Yes.
About 3.
Yeah, what did your decimal say?
2.994.
Beautiful. 2.994 cups of sugar. Okay. So the flours cancel. To keep this in the right proportions, you guys know when you cook, you have to have things, if you want it to taste the same, you have to have things in the right proportions to each other. Sometimes it's easier than others, but when you start throwing in 2/3 and halves and stuff, it gets a little messy. Okay, we'll pick up tomorrow with the calculations on the next page, and hopefully we won't get through this whole packet, but we'll get through a couple of them. Okay, and Jack brought us brownies.
They're gluten-free too.
Oh, wow, getting fancy.
Our household.
The whole house?
Yeah, my sister's allergic to them.
Everybody has to suffer because you're a sister, huh?
We get some gluten sometimes.
Oh, you didn't cut them and you made Chopper, you
Never said you
have someone's gonna get them.
Oh, okay. So I came here 0 period and your classroom wasn't open. Well, I thought you said that. so
Not 0 period.
so I was sad and then I can't really bring them over.
Oh, I have really small ones. Okay. And bounce it out here. Okay, here, come have some of Jack's brownies. Jack's gonna wash his hands and distribute them.
I have one.
They're also not gonna ruin this cold.
That's like,
You guys are being mean to each other.
it's like, probably like, oh, I'm sorry. I don't know. Sorry to
Well, we started too.
Sorry.
Thank you, Jack.
Thank you, Jack.
I'm just nervous.
Thank you, Jack.
Thanks, Jack.
Of course. I'm sorry if you're mad.
Thank you, Jack.
Yeah, there was
Brownie, that's brownie.
I know, that's enough. Thank you.
We'll get one. There's lots more brownies.
I'll compare them.
And-
Wait, do I still get extra credit if I didn't bring them in? Oh, actually, I'm like, I wrote the equation.
Yes, you wrote the equation on it.
And I didn't, I took a picture.
Thank you, Jack.
Thank you, Miss
Oh,
Goodman.
Bye. There you are, sir. You can take your brownies to your next venue. Thank you so much.
You want one?
I'm good. I'm too fat as it is. Thank you, my dear.
Yes. Have a good day.
Thank you,
too.
Mrs. Goodman.
Thank you. Sorry, and Caitlin. See ya. Bye, Anthony. If you're still here. Thank you. Bye.